we on the organizing committee had wanted to get representation from federal agencies around the world about their future plans for missions, to understand what we might have a chance of discovering in the near term from these missions. And so we're going to start with NASA, and Jim Green, who's the chief scientist there, to talk about what those NASA missions will tell us about life in the universe. So, Jim?
Thanks so very much, Jill, for giving me the opportunity to give an update on what NASA is doing in the area for searching for life. And what I'd like to do is break it up into a couple sections. I first want to talk about planetary missions. So that's typically looking for life in our solar system. And that comes in several lines, mission lines, the Discovery, New Frontiers, but also our strategic missions. And then in the area of astrophysics, looking for life in exoplanets, I'll talk briefly about TESS, the Transiting Exoplanet Survey Satellite, James Webb, but also Nancy Grace. And then I'd like to end with a comment about what is our confidence for life detection as we move forward. So in planetary science, we have, as I mentioned, several lines of missions that we fund. This is approximately $450 million mission minus the launch vehicle currently. That's our Discovery missions. We've had a series of fabulous missions. Many don't know, but actually Kepler was a Discovery mission selected in a round in 2009, and then eventually transferred over into astrophysics to complete and manage. In that same line, we have now just selected and announced in the Discovery line the mission DAVINCI Plus, and that will explore our past and present Venus. DAVINCI is all about a deep atmosphere Venus investigation of noble gases, chemistry, and imaging. And it is structured in a way where it has two major components. One, indeed, is a probe that will descend in the atmosphere, take a whole variety of measurements with its mass spectrometer, its tunable laser spectrometer, and other imaging systems through that atmosphere, and a carrier satellite, which will also be used to receive the probe's signals and transfer them back to Earth. It will also have a variety of context imaging going on the carrier. Now, of course, within the last year and a half or two, there's been quite a bit of discussion about potential phosphine in the clouds, upper clouds of Venus. DAVINCI, when it was proposed, wasn't designed to be able to make phosphine observations. However, I will mention that it's in discussion. The PI, who is Jim Garvin, believes that they can be able to do that, but we'll see how that evolves over the next several years. Now, in addition to the Discovery set of missions, we have the New Frontiers class of missions. So these are close to $1 billion missions. We execute 2 or so every 10 years. And indeed, the last selection, New Frontiers 4, I was head of planetary science at that time. And because of the rapid discoveries going on, in particular, the concept of the ocean worlds of moons of these giant planets, and Titan in particular, as we began to learn so much more about it, when went back to the National Academy of Sciences and got their approval to enhance the number of focused missions that we would accept proposals for in New Frontiers. And once again, that is a set of missions that are close to $1 billion, but well focused. We have certain targets. And delighted to say that Dragonfly, which is a Titan drone, was selected. Now, Dragonfly is a quadcopter, so to speak, that will really hop around, interrogating more than 24 or 25 unique landing sites. in each of its hops. Its science objectives are to analyze the chemistry and look at the processes, particularly those that relate to biological relevant compounds. Also measure the atmosphere and surface conditions, constrain processes that mix organics with water, and search for the chemical evidence of biological processes. So a tremendous mission to be launched in 2027, arrive in 2030 at the large moon Titan. And of course, Titan is larger than the planet Mercury. Its atmosphere is about twice the pressure we have here. And it's therefore makes it an easy ability to descend and then begin to examine and interrogate the environment with Dragonfly. Let me now shift towards our operating missions at Mars and our upcoming plans as we move forward. You know, it's phenomenal to see the large array of multinational missions that are orbiting Mars, and those, of course, that are on the surface that are working. These are all the operating missions that are currently taking significant amounts of data simultaneously. And as we continue then to work in our open data systems and work with our international partners to be able to do that, we anticipate drawing more information from the ability to correlate many of these missions. I want to talk about a couple of them. One is Curiosity, which has been on the surface since 2011, and also Perseverance. Now, what we've learned from Curiosity, this is a 1-ton rover designed to really interrogate the soils. Here we have a drill that goes in and pulverizes material that goes down a 1.5 centimeters or so with the hole size diameter about the size of a dime. And what we see as we begin this process is we see below that patina of red oxidized surface, significantly different colored soils. And in fact, as we bring them into the sample analysis of Mars, or SAM instrument, we really look at them and we find that the mineralogy indicates sustained interaction with liquid water. And of course, that is very important because of the providing a source of energy for primitive biology. We also find the key chemical ingredients for life are present. So that's carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. The soils are moist and they have nitrates. One of the really fantastic discoveries Curiosity has made is in the area of diverse organic structures, including micromolecules, benzene and propane, but they're also part of macromolecules like the kerogen. And on Earth, typical organic constituents of kerogen are really algae and wood plant materials. Just a fantastic discovery in this area that these molecules indeed are preserved at some level and in some way. Methane, we've been noting Mars emits methane for several decades now, but being on the surface, Curiosity has indeed measured major amounts of methane in terms of it always being above the background and cyclic with the seasons, having seen more methane during the summer months. Of course, methane can be generated biologically or abiotically. And it could be ancient methane also, trapped below the surface in clathrates, for which during the summer months, as the soils are heated and then the frozen nature of the surface changes because of that heat, allowing some of the methane to leak out. Could be what's happening. We don't have enough of that methane to come in and really tease out isotopic ratios and do a number of next step things that we'd like to do to probe whether this methane is abiotic or biologically generated. Also, the radar observations indicate underground liquid water. Here's one of the first what we'd call lakes observed at 1.5 kilometers below the surface, on the order of 20 kilometers wide, seen by Mars Express. And the concept is perhaps this is part, of course, of an underground aquifer system. The end result is that indeed we now know Mars has a significant amount of water locked in its crust. And we understand as we connect together all the observations over long periods of time that we believe Mars was a blue planet early on. At about 3 billion years ago, it went through rapid climate change and became the arid planet it is today for several billion years. And so by going to Mars now and interrogating Mars, we're actually looking at these ancient surfaces with the ancient potential for early biology to have occurred, since this is approximately the same time frame that microbial biology began here on Earth. So where are these discoveries leading us? Well, it really is telling us that the potential for ancient life is increased. Lots of sign of ancient water on surface, but also subsurface, past geological environments that have reasonable potential to have preserved that evidence of life is existing. And the detection of these complex organics has increased the potential for preserved fingerprints of life. So we now have a means, because of the massive amount of network of orbiting satellites with high resolution imaging and mineralogy, to really determine candidate landing sites. And we have reason to believe that evidence that we are seeking may be preserved within each of these exploration systems that we can develop and deploy. And therefore, the big next thrust for Mars research has been Mars Sample Return Campaign. Now, the start of that sample return campaign is really the Perseverance rover. And Perseverance landed on Mars this year in February 18th. It has a significant number of instruments that look at the subsurface through its radars, but also high resolution cameras looking at mineralogy, and also LIBS instruments, X-ray spectrometer, you understand mineralogy in the context, and then a core that drills cores, generating samples about the size of a chalkboard chalk that then is put in a metal tube. And we have 43 sample tubes that can contain up to 15 grams of Mars sample material. Now, we've landed safely Perseverance in Jezero crater. Jezero crater is a fabulous structure for which we see rivers that have flowed into this crater, filled up, and then busted out its northern crater rim wall into a larger basin which fed the ancient ocean of Mars. And so the rapidly flowing river water, dropping its silt because of the still water in Jezero crater, produces a fabulous delta. This delta is about 10 kilometers in diameter, and it has quite a diversity of mineralogy as we observe from orbit. And of course, Perseverance is sitting there now just on the south side of the delta, interrogating the crater floor, and is beginning the process over the next year or so to begin going up the delta. The delta is about 65 to 70 meters thick. And so we'll really have quite an opportunity to examine samples of potential life that have been deposited in the delta over time. If it's there, we hope to be able to get the right samples. Now, of course, the rock samples are extremely important. Here on Earth, there's more than 5,000 minerals. And about 330 or more of those known materials are really formed by interaction of organic remains. And therefore, the rock sample will indeed, we believe, provide us information not only about the geological history and how the planet has changed over time, including perhaps some indication of how rapid the climate change occurred, but preserve that ancient life. And in fact, then perseverance is really all about looking at the ancient potential for ancient microbial life by looking at the geology, the astrobiology, caching those samples. And it has some human exploration instruments that I won't talk about that feed forward into future missions, potentially for humans. But how are we going to bring these samples back? As I mentioned, perseverance is the start of this process. And what we want to do now is we want to have an architecture of several missions. Mission 1 will launch probably in the 2026 timeframe. It'll have a Mars ascent vehicle along with a fetch rover. The samples will be dropped in certain key strategic locations that will be picked up by the fetch rover, brought over to the Mars ascent vehicle. That will be erected, launched. Mission 2 will be able to hunt that sample down in orbit, and that sample cache will then be brought back to Earth and land in Utah, for which then it will go into a biosafety level facility. So that will begin the analysis of fabulous samples that are brought back from Mars. Now, in addition to that, perseverance and Mars activity looking for life through the rock record, is we also have the Europa Clipper mission. This is a follow-up on so many fabulous observations of this moon by not only Voyagers, but Galileo and Hubble, which has observed what we believe are plumes, a series of plumes. We also see the significant variation in the surface terrain, widely suggesting different active processes such as potentially hydrothermal vents. And then, of course, what we want to do is we want to be able to find the plumes, fly through them. We want to be able to look at the ice ocean processes. We have a feed forward instrument. It's a very high resolution imager looking for future landing sites, because potentially our future missions may be landing near plumes, but also potentially going under the ice shelf or into the ice cracks in some way, looking for also a potential life in the future. As we switch to astrophysics, TESS, the Transiting Exoplanet Survey, here's just one of an early announcement that they had of a fabulous discovery of sextuple eclipsing solar system. TESS is keeping count, of course, of the confirmed planets and also the planet candidates, several thousand of them now, and is really following up on where Kepler left off. TESS looks at bright stars. Bright stars are closer to the Earth by nature, and therefore those candidate observations indeed can be those that could be considered by James Webb Space Telescope to be able to follow up. Now, what Webb does, of course, is it has 4 major goals, looking at light from the first galaxies and the assembly of galaxies, but also the birth of stars and planets and exoplanets. And in particular, we wanted to look at the atmospheres. Detecting exoplanets by observing the starlight, like Kepler and TESS, that's important. That finds our candidates, but really detecting life signatures now means we have to tease that out of the planet's atmosphere itself. Now, we'll remind everyone that it goes to a very different orbit. It's Lagrangian point 2, which is behind the Earth at about 240 Earth radii away. And it has a tortuous route in the sense that over a 2-week period after its launch, it unfurls and goes through a variety of tests. And so it's going to take not only a while before it gets there, but it will take several months, of course, to commission and get ready before it can really begin operating in a normal mode. The current launch date has just been announced to be no earlier than December 22nd. So it's coming up quite quickly. also in the future is the Nancy Roman Space Telescope. And this is also another spectacular mission because it has a couple ways it looks for exoplanets. And I'll mention that indeed it has very sophisticated diffraction masks that then will block out the starlight, and with the intention of being able to find those planets and begin to study them in this manner. Now, the astrophysics decadal has just come out. It's a rather aggressive decadal. It leans forward in a really nice way. It's really has importance of the future telescopes for habitable exoplanet observations. They want to optimize that. That means there are a number of technologies that have to be developed. They delineated those. They want NASA to begin rapidly investing in those technologies to get ready for when indeed they will be mature to start a series of telescopes that could be launched covering these wavelength regimes. And indeed, one of the top large telescopes, a 6-meter off-axis IR optical and UV telescope, is one of the important ones they want to do for observing exoplanets. Now, in summary, let me mention that in addition to a whole series of missions that NASA is working on, both in planetary and astrophysics, I will note that we recently put out a paper about the field of how we talk about biosignatures and how we relate not only between our scientists in terms of where we are and the confidence of those measurements, but how we might be able to do a better job in communicating not only the right excitement, but putting it in context with the series of steps that we think are so necessary to provide us information about standards of evidence for life detection, building that confidence that each measurement we make reaches towards a goal. Now, one can go up this scale that we proposed or down the scale we proposed. This is not the right scale, but we asked the community to begin that process of discussing this as a potential process for these biosignature measurements and the confidence we will have in making these measurements. And the community's responded with a wonderful workshop that came out in July of this year, and in Biosignature Standards of Evidence Workshop, and that report is currently online. So I think these are the top areas that we're making major progress in, and so let me thank you and turn it over back to Jill.
Thank you, Jim. Thanks a lot. We only have essentially a minute or so for questions, and the ones that I've been seeing are, okay, you got 1.5 generations of astronomers and astrophysicists waiting on JWST. What today are the chances that we'll actually launch in December?
Good question. As many probably know, there was an anomaly that occurred by a fastener that broke unanticipated. That creates a little shock. You know, we go through our systems with a range of acoustics. The acoustics are known for our launches, and therefore we build our missions to that. We're looking at what happened in that event. That analysis should be complete, we think, within the next week or so. But indeed, we needed the time to do that. So although the launch date was the 18th and it's moved to the 22nd, we'll know more firmly whether we can meet that date within this next week, we believe.
Well, fingers crossed. It's been a long
Fingers
time.
crossed. Absolutely. Thank you.
And then another question is regarding the methane on Mars that you spoke about. What's needed to figure out if that has a biotic or abiotic origin?
Well, SAM has the capability to measure the isotopes. And the isotopes, of course, of methane, the one that's most interest is the carbon 12, 13, 14. We know has a natural occurrence, but life loves carbon 12. If we can bring in the methane and make a measurement of all the isotopes within a significant amount of methane that we could hold, then we can determine if it has a natural sequence of carbon 12, 13, 14, or if it is imbalanced with a large amount of carbon 12. Now that only gives us a little bit of information or confidence that it may be generated by life, if indeed the isotopes help support that. But that will spur us on to be able to do a better job finding its origin, and maybe it's collecting in certain regions, perhaps matching aquifers or something. And certain missions can be thought of in terms of how we would go about that and how then we drill below the surface looking for the methane, particularly if we can find concentrations of where it's leaking through the surface. So I have much to do in that area.